Okay, hi Riyashat. Am I audible?
Yes, sir.
Oh, okay. So, any doubts from last class? Okay, so let's wait a couple of minutes for others to join. Then we'll start.
Good evening, sir.
Yeah, good evening, Siddharth. So, you will be appearing for GATE exam in this year, right? Like next February, right?
Sir,
Oh, okay. Okay, now we can start, I think. So, first introducing myself again, I'm Shubhadeep and I am doing my PhD at IIT Kanpur, and this is my second year. Okay, so today also we will be solving three questions, question number 43, 53 and 54 from 2020 chemistry paper. Okay, so let's start. So let me just share my screen. And while solving, if you have any doubts, you can unmute yourself and ask. Without any hesitation, you can ask any questions. Okay, so is my screen visible? Anyone just?
yes, sir, your screen is visible.
Yes, sir.
Okay, thanks. Okay, so let's start. So this is question number 53 from 2020 paper, and the question is, at 30 degrees centigrade the vapor pressure and the density of 1 molar aqueous solution of sucrose are 31.207 millimeter Hg, and the density is 1.1256 gram per ml. So the vapor pressure of pure water at 30 degrees centigrade is also given, 31.824 millimeter Hg, and we have to find the activity coefficient of the given of water in the given solution. The molar mass of sucrose is also given, 342.3 gram per mole. Now, so we have sucrose solution, molarity of our solution is 1 molar, and the pressure of the solution P and the vapor pressure of the pure solvent, that means water, P0 is also given. Density is given. Now we have to find the activity coefficient. So basically the expression of activity coefficient is, okay, activity coefficient basically is expressed by gamma, symbol gamma, and the expression is A equal to gamma times x1. That means A is the activity of solvent in our solution, gamma is the activity coefficient, and x1 is the mole fraction of the solvent in our solution. That means mole fraction of water in our case. So we have to find this gamma, that means gamma equal to A divided by x1. So first we have to find the activity A, then we have to find the mole fraction chi1, then we can divide the A with chi1, then we can find we can get the value of activity coefficient gamma. Okay, so first the activity of solvent, that means in our case water in a solution, is expressed by this expression P divided by P0. That means activity equal to ratio of pressure of the solution at a particular temperature divided by the vapor pressure of the pure solvent. So here P is the vapor pressure of the solution, and at 30 degrees centigrade, let's say, and P0 is the vapor pressure of the pure solvent at 30 degrees centigrade. So we know the value of P and P0, so we can find the activity A. So A will be equal to just P means 31.207 and P0 means 31.824. So the ratio is 0.98. So the activity of the solvent, that means water, in our solution is 0.98. Now we have to find the chi1, that means the mole fraction of our solvent, that means water, in solution. So to find chi1 we have to start with the density. So density is, we know the density equal to m divided by v, that means the mass of the solution, total mass of the solution, and the v is the total volume of the solution. So so density equal to m divided by v, where m is the total mass of our solution and v is the total volume of our solution. Now let's say in our solution the m1 gram of solvent is there, this is solvent, and m2 gram of solute is there. That means m1 gram of water and m2 gram of sucrose. So total mass m will be just m1 plus m2. Now we can express the m1 gram in terms of number of moles and the molar mass. So m will be equal to n1 m1, where n1 is the number of moles of solvent present in the solution, and capital M1 is the molar mass of the solvent, that means water. Similarly, m2 will be equal to just n2 times m2, that means number of moles of sucrose times the molar mass of the sucrose. So this will be the total mass of our solution, m. Now so we can redefine the D equal to n1 m1 plus n2 m2 divided by total volume of our solution. Now let's say so we know that here we have said that in our solution n2 moles of solute are present. So in VML solution, so total volume of our solution is VML. So in VML solution, n2 mole of solute, that means sucrose, is present. So in 1000 ml solution, how many moles of sucrose will be present? n2 times 1000 divided by V. So this the number of moles of sucrose present in our solution in 1000 ml, that means the molarity of our solution. So molarity is expressed as the number of moles present in 1000 ml of our solution. So this will be equal to our molarity of our solution. Let's say it is capital M. So molarity of our solution, capital M, will be equal to just n2 times 1000 divided by V. So the capital M is n2 times 1000 divided by V. So we can redefine n2 by V from this expression. So n2 by V equal to M divided by 1000. Now in the expression of D, we can put this value. D will be equal to n1 capital M1 divided by V plus M capital M2. N2 by V, we can put this value M divided by 1000. So it will be equal to M capital M M2 divided by 1000. So then from this expression we can find the expression of N1, that means number of moles of solvent, that means water, present in our solution. So N1 will be equal to just 1000 times density times V minus V capital M capital M2, so this negative sign will be noted here, divided by the 1000 times M1. So now the mole fraction of solute, that means chi2. So the expression of defining the mole fraction is the number of moles of solute present divided by the total number of moles present in our solution. That means N1 plus N2. So N2 is the number of moles of solute present in our solution. N1 is the number of moles of solvent present in our solution. So chi2, that means the mole fraction of our solute will be equal to N2 divided by N1 plus N2. So we know all the expression of we know the expression of N1 now from this expression. So we can put the expression here in the expression of chi2. So chi2 will be equal to just M, capital M, which is the molarity of our solution, times capital M1, that means the molar mass of the solution, divided by 1000 times density minus capital M and the M2 minus M1. Now we know here in this expression, we know all the values. If you see the questions carefully, capital M, that means molarity of the solution, which is 1 molar, it is given. Capital M1, that means molar mass of the solvent, that means water in our case. We know the value 18 gram per mole. D means density of the solution. We know 1.1256 gram per ml. Again M2, that means molar mass of the solute, that means sucrose in our case. So M2 is also given 342.3 gram per mole. So we can put all these values in this expression and get the value of chi2, that means mole fraction of solute present in our solution. So chi2 is will be equal to 0.02246. Now to express to get the value of activity coefficient, we know we have to find activity and chi1, mole fraction of solvent. So we know we got the value of A, which is 0.98. Now we have to find the value of chi1. Now we got the value of chi2. So in our solution we know that the total mole fraction, that means the mole fraction of solute and the mole fraction of solvent, summation of all these mole fraction will be equal to 1. So we know the chi1 and chi2 will be equal to plus chi2 will be equal to 1. We know the value of chi2. Now we can get the value of chi1 from this expression. Chi1 will be equal to 0.97754. So this is the mole fraction of solvent, that means water, in the sucrose solution. Now activity coefficient is A1 divided by chi1. So gamma will be equal to 0.98, that is A1 mole fraction A, so mole fraction of solvent in our solution, times the mole fraction of solvent in our solution, which is 0.97754, which is 1.0025, and up to third decimal places it will be equal to 1.003. Why? Because in third decimal places it is 2, and after this place, after the third decimal place, it is 5. So if it is 5 and greater than 5, then we can round up this value, third decimal place value, plus 1. So 1.003, 2 plus 1 equal to 3. If it is below 5, then we have to keep the value 1.002 only. So the correct answer will be the activity coefficient of water in the given solution is 1.003. Okay, so got it? Any doubts from this question? So basically we have to remind the first two expression, that means the expression of activity, the expression of activity, that means A, which will be equal to P divided by P0. That means any quantity, any colligative properties, let's say, or the concentration in our solution, we can express also in terms of concentration also. So activity will be equal to just P divided by P0. That means vapor pressure of a solution and divided by the vapor pressure of the pure water or pure solvent at that temperature. Okay, so then by getting the value, after getting the value of activity, then we can find the value of chi1, that means mole fraction of solvent, Then with value of A and chi1 we can find the value of activity coefficient. Okay, so now let's solve question number 54. So question number 54 says, for the ring opening reaction of cyclopropane to propane, that means the reaction is cyclopropane to propane at 25 degrees centigrade, that means room temperature. The pre-exponential factor is given, which is 4.3 times 10 to the power 15 second inverse. Look at the unit carefully. It can also the unit of pre-exponential factor is second inverse. That means in general it is 1 upon time. So this is important actually. The entropy of activation in joule Kelvin inverse mole. So we have to find the entropy of activation. So the H, that means the Planck constant value, is given 6.66 into 10 to the minus 34 joule second. The Boltzmann constant value is also given, that means Kb, which is 1.38 times 10 to the power 23 joule Kelvin inverse. And the value of universal gas constant, that means R, which is also given 8.314 joule Kelvin inverse mole inverse. It is in SI unit. Now for any reaction profile, that means for any reaction, chemical reaction, let's say it is the reaction is happening along a one particular coordinate. We call it a reaction coordinate. That means along that coordinate the reaction is happening. So the reaction profile will be, that means let's say it is y-axis, it will be energy, and in x-axis we represent by reaction coordinate, any reaction coordinate, let's say R. And the reaction is happening from reactants to product, that means like this. It is one dimensional, let's say. So here the reactants, here are the products, and this is the transition state. We call it an activated complex. So just a little bit of background. This is called the activated or activated complex because this or before that, this energy difference, because that energy of transition state or activated complex minus energy of reactants, we call the this difference of energy is activation energy or EA. Now this is called activated reaction because the activation energy, that means EA, this difference has to be greater than the thermal fluctuation happening at the temperature, at the reaction temperature, that means 25 degrees centigrade in this case. That means when the reactants are in this well, that means in the reactants well here, so they are in equilibrium, right? So at 25 degrees centigrade there will be random thermal fluctuation. So for activated reaction, that means the reactants molecule has to be activated to form products. It means that the random fluctuation cannot actually transfer the reactant molecules to the product immediately. So it has to be activated. That means the difference in energy from activated complex to reactant molecules, that means the activation energy has to be greater than the random thermal fluctuation, that means KBT. Then we call it an activated reaction. Otherwise the random thermal fluctuation at any temperature, at the particular temperature, can actually transform the reactant molecules into products. So there will not need of any activation. So that was a little bit of detour here. So for this question, actually we have to find the entropy of activation. What is the entropy of activation? Let's say this is the reaction profile, A for the reaction A plus B to C. Here A and B are the reactant molecules and the C is the product molecule. Let's say in this case it is P. and before reaction actually the reactant molecules A and B actually combine or form an activated complex. Here let's say we call it the activated complex or the transition state with AB double dagger. So this is the activated complex. Now the difference of energy between the transition state or activated complex and the reactant molecule is the activation energy or EA. Now entropy of activation means, let's say, delta S double dagger. Entropy of activation means the entropy of activated complex, that means AB double dagger, minus entropy of reactant molecules. This difference is the entropy of activation. So we have to find this delta S double dagger. Okay, so let's find this. Now we have to impose the transition state theory approximation here. So in transition state theory, it is approximated that, it is assumed generally that the activated complex, that means AB double dagger, and the reactant molecules, that means A and B, are in equilibrium. So this AB double dagger and the reactant molecules A and B are in equilibrium with each other. So okay, so these two are this activated complex AB double dagger and the reactant molecules A and B are in equilibrium with each other. So as they are in equilibrium, so we have an equilibrium constant. Let's say the equilibrium constant in this case is K double dagger. So from thermodynamics we know that any equilibrium constant, we can express the equilibrium constant K double dagger will be equal to just the concentration of product divided by the concentration of reactants. So equilibrium constant in this case K double dagger will be equal to just AB, concentration of AB double dagger, that means concentration of the activated complex, divided by the concentration of reactants, that means concentration of A times concentration of B. Now for the rate of the reaction for the product formation, that means for this step actually, from activated complex to product formation, from chemical kinetics we can write the rate equation for this step. So rate equation will be just dp dt, that means the change of the rate of formation of product P with time will be equal to just some rate constant, let's say it is kp times the concentration of activated complex AB double dagger. So dp dt will be equal to just kp times AB double dagger. Now from this equation we can find the concentration of AB double dagger, so which is AB double dagger will be equal to just K double dagger times A times B. So kp times K double dagger, concentration of A, concentration of B. So now we can combine these two rate constant, which kp is the rate constant for this step and the K double dagger is the equilibrium constant for this step. So let's say it is K. So K is the overall rate constant for the reaction A plus B to C or P, let's say. This is the overall rate constant. So K is Kp times K double dagger. Now for statistical mechanics calculation, we can from partition function we can find the expression of K. So I will not go in detail here. So K will be equal to Kp here. K will be equal to just Kbt divided by H. This is the Kbt divided by H times K double dagger. Now as K double dagger is the equilibrium constant, that means for this step A plus B, they are in equilibrium with the activated complex. This is the approximation in transition state theory. So this equilibrium constant is K double dagger. So K double dagger is we can express from thermodynamics. We know that any equilibrium constant equal to it exponential minus delta G double dagger divided by RT. So delta G double dagger here is the free energy of activation. That means the difference of free energy of activated complex, that means AB double dagger, minus the reactant molecules. So delta G dagger here is the free energy of activation, R is the universal gas constant, and the T is the absolute temperature at which the reaction is happening. Now we know the relationship between the delta G dagger and the enthalpy and entropy. So delta G double dagger will be equal to delta H double dagger minus T delta S double dagger. So delta H, similarly the change in enthalpy of activation, that means the enthalpy of activated complex minus enthalpy of reactant molecules, and delta S double dagger is the activation entropy. So we have to find this delta S double dagger. So now we know that K the total overall rate constant K equal to Kp times K double dagger, which is the kBT divided by H times K double dagger. Now from this expression also an interestingly in TST, that means in transition state theory approximation, rate constant K is proportional to temperature. The pre-exponential factor is proportional to temperature. We'll find this in later. Okay, so K equal to now kBT divided by H. We can put this expression here in place of K double dagger. So e to the power minus delta S double dagger divided by R times exponential minus delta H double dagger divided by RT. Now we know the relationship between the enthalpy of activation and the activation energy, that means EA. Relationship between the EA and enthalpy of activation delta H double dagger. This relationship is EA equal to delta H double dagger plus RT. This is an important relation. Okay, I will derive it later. So we can delta H double dagger will be equal to EA minus RT. So we can put this expression here by replacing this. So overall we can write A times e to the power minus EA divided by RT, where EA is the activation energy and A is the pre-exponential factor. Now combinedly the expression of A is this kBT divided by H times e to the power delta S double dagger divided by R plus 1. So by looking at this expression, you know the in TST, using the TST expression, that means the transition state theory approximation. What was the approximation? Approximation was the reactants and the activated complex are in quasi-equilibrium or equilibrium. In TST approximation, pre-exponential factor is proportional to temperature. This is actually important. Now from this expression we can get the expression of delta S double dagger, which is needed. Delta S double dagger is the entropy of activation. We have to find this value. So it is equal to R times ln. So bracket is this. Yeah. R times ln H divided by kBT minus 1. So we know all these values. We know the expression value of pre-exponential factor A. In the question it is given. H, that means Planck constant, we know the value. kBT is we know. T is the absolute temperature, that means reaction is happening at 25 degrees centigrade, means in Kelvin scale it is 298 Kelvin. So we also know this value. After putting all these values, the delta H dagger is 46.499. After 2 decimal places rounding up, we can get the value of 46.60. And the unit of entropy is, we know, the joule, mole inverse and Kelvin inverse. So for this question, the entropy of activation will be equal to 46.60 joule Kelvin inverse mole inverse. Okay, now for further details on these topics like chemical kinetics and transition state theory, you can visit the Nptel lecture series on the topic of chemical kinetics and transition state theory by Professor Ambar Jain from IIT Mumbai. Okay, so any questions from this question? Any doubts?
No, sir.
Okay, so you all know the relationship between the activation like this. Okay. You all knew this relationship, right? Activation energy and the enthalpy of activation. Anyone? Did you know? Actually, it is an important relationship. So the activation energy and the enthalpy of activation. Anyone? Just yes or no?
No, sir. It's completely no.
Okay, so do you want me to derive this? Actually, this is a two-line derivation, so I can show actually. Okay, so let's just derive it. Okay, so first let's write okay. So this is really an important relationship. It is. So let's first write the activation pre-exponential factor. We know that the okay, we know from Arrhenius expression or any transition state theory, from transition state theory we know the rate constant. We can express the rate constant K equal to A times e to the power minus EA divided by RT. So A is the pre-exponential factor, and also here we write we got the from TST we got the expression of A is KBT divided by H e to the power delta S double dagger divided by R plus 1. Okay, so K is equal to this and K is equal to this. So now let's take ln of both sides of K. Now from this expression, first use this expression, which is equal to ln A minus EA divided by RT, right? Now from this expression, ln K equal to ln of KBT by H plus delta S double dagger divided by R plus 1, right? Now let's take derivative with respect to temperature. That means d ln K by dt should be equal to, this is a constant, A is a constant now. So in the time derivative with respect to temperature, with respect to temperature, it will be equal to 0. From Arrhenius, this expression is for Arrhenius expression and this is for transition state theory expression. So this will be equal to 0. Now for this term we have to take the derivative. It is 1 upon temperature. So if we take derivative with respect to T, it will be equal to just 1 upon minus 1 upon T square. So minus minus will be plus. So EA divided by RT square. EA is the activation energy. Now in this case also let's take the derivative d ln K by dt will be equal to, here the temperature is there, so we can the KB and H are the constant, so we can re-express this expression as ln KBT divided by H, which will be equal to ln KB by H plus ln temperature, right? It is log, so we can express the multiplication with summation. So this term is constant, it will be equal to 0 with, upon taking derivative with temperature. So this is ln T, upon deriving derivative with temperature means it will be equal to 1 upon T. And this is will be, so delta is double, I'm sorry, and, so it is multiplication of e to the power minus delta G double dagger by RT, it will be there now. Okay, So now it will be equal to just plus delta G double dagger divided by RT square. Now this side also, it is the time derivative of d ln k, d ln k by dt, and this side also, it is also d ln k by dt. This side from Arrhenius expression, and this is for transition state theory approximation. Now we can equal these two terms, d ln k by dt and d ln k by dt. So it will be equal to just EA divided by RT square from this side equal to 1 upon T plus delta H double dagger divided by RT square. So EA will be equal to multiplied by RT square, so it will be equal to RT plus delta H double dagger. Okay, got it? Okay, so any doubts? So from this we can find the expression of EA and the delta H double dagger. That means activation energy and the enthalpy of activation. So we are using this expression in the in solving this question actually here. Okay, so if there are any doubts, so we can. Got it, no? There is not any doubts, no?
No, sir.
Okay. Okay, so now let's solve question number 43. Okay. So this is question number 43 from the 2020 paper, and the question is about the adsorption of a gas on a solid surface. So adsorption of N2 gas on Ti2 surface was carried out at 75 Kelvin. A plot of Z divided by 1 minus Z times V versus Z, where here the Z is P divided by P0, gives a straight line with an intercept 4.0 times 10 to the power minus 6 millimeter minus cube, and slope is also given 1.0 times 10 to the power minus 3. So we have to find the volume corresponding to the monolayer coverage rounded up to the nearest integer. So this is actually about the adsorption. Last time we said that the adsorption of a gas, basically nitrogen gas, on a solid surface, which is the TiO2 surface at particular temperature 75 Kelvin. Now a plot of this versus this is given with it is a straight line plot, which is intercept and a slope. Now we know that for adsorption of any gas on a surface, we know we can use two types of expression, like Langmuir isotherm, expression for the Langmuir isotherm, and the expression for the BET isotherm. Now Langmuir isotherm is basically for monolayer adsorption. That means when the gas molecules are adsorbed only one layer after the surface, solid surface, on the solid surface. So Langmuir is basically monolayer adsorption. And for multi-layer, in reality, what is happening in reality, actually on solid surface, when gas adsorb, so they actually adsorb on multiple layers on the solid surface. So we have to consider the multi-layer adsorption process to simulate to capture the actual effects. So for multi-layer adsorption, we use the BET isotherm, which is the BET equation. Now we are not deriving here the BET equation. So the BET equation is Z divided by 1 minus Z times V equal to C minus 1 times Z divided by C times V monolayer plus 1 divided by C times V monolayer. But C is a constant, and the C is basically exponential E1 minus EL divided by RT or kBT. Now E1, which is what is E1? E1 is basically the heat of adsorption for the first layer. Like let's say this is solid surface and nitrogen gas is adsorbing here. For the first layer, the heat of adsorption is E1. Now for other layers, apart from first layer, let's say like this, the heat of adsorption will be equal to EL, which is equal to heat of liquefaction or vaporization. Why? Because in bait isotherm we use an approximation like the heat of adsorption, the interaction energy between the gas molecules here and the solid surface for the monolayer is strongest. Like you can assume that or visualize that the interaction energy between the gas molecules on the monolayer and the solid surface is high or is large, and the interaction between the gas molecules and the gas molecules on different layers, that means second layer and first layer and the third layer and the second layer, which is very small compared to the gas and solid interaction. So all this interaction between all these layers apart from first layer, that means second, third, fourth, fifth interaction, we assume it is equal to the heat of liquefaction. That means heat of liquefaction or vaporization, and the heat of adsorption is E1, we assume that. So it is different and EL is different. So C is a constant, so this is the bait equation. So the Z here is the P divided by P0, where P is the pressure of the gas, that means at which pressure the gas molecules are adsorbing on the surface, and the P0 is the saturation pressure, that means liquefaction pressure. When after this pressure, at the saturation pressure, the liquefaction starts. So P0 is the saturation pressure and the P is the pressure of the gas. So look at this equation. This is an equation like y equal to mx plus c, where y is this, x is z, and m means slope will be equal to this term, and c means intercept, that means this term. So if you plot the y versus x, that means this versus this, we can get a slope and an intercept. So the value of intercept and the slope is given, so we have to find the volume of the monolayer coverage corresponding to the monolayer coverage. So here in this expression, this V mono, that means the volume of the gas corresponding to the monolayer. So it is the volume of the monolayer coverage. So intercept is given, that means 1 divided by C times V monolayer is given, which is 4.0 and 10 to the power minus 6. Slope is also given, C minus 1 divided by C times V mono, which is 1.0 times 10 to the power minus 3, it is given. Now from this expression, like C minus 1 times 1 divided by C mono, we can write this. So this is the expression of intercept, so this value is known. So now put this value here, C minus 1 times 4.0 times 10 to the power minus 6 equal to 1.0 times 10 to the power minus 3. Now from this expression we can get the value of C. C is the 251, which is the constant of the bait equation. Now using this intercept equation, we know the value of C here, so we need to find the value of V mono. So V mono will be equal to just 1 divided by 251 times 4.0 times 10 to the power minus 6, which is 996 millimeter cube, the nearest integer value. So volume corresponding to the monolayer coverage is 996 millimeter cube. Now for a side note, actually let's say from the bait is basically multi-layer adsorption process, and the Langmuir is basically monolayer adsorption process. Now for bait, there are, let's say this is solid surface, there are gas molecules. So for the interaction between the first layer and the solid layer is different compared to the interaction between the second, third, fourth, fifth, etc. Now for each layer, like let's say for third layer, for fourth layer, for fifth layer, for first layer, for each layer we can use the Langmuir isotherm. that is Langmuir is monolayer adsorption. So for each layer we can use the Langmuir isotherm. So and also for Langmuir isotherm, it is approximated that the neighboring sites are not interacting, that gas molecules in the neighboring sites are not interacting with each other, that because there is no interaction in Langmuir isotherm, it is considered that the gas is ideal. That means there is no interaction between the gas molecules on the neighboring site. Let's say this is solid, this is site 1, this is site 2. Gas molecules is adsorbed here, gas molecule is adsorbed here. So there will be no interaction between this site gas molecules. And in the Langmuir isotherm, it is also approximated that all the surface sites are equivalent to each other. In reality, what we will see in a solid surface, it is not homogeneous, right? There will be many defects. So surface is actually heterogeneous. So that means all the sites, adsorbent sites on the surface will not be equivalent to each other, because for some sites, let's say for this side the gas molecule, the adsorbing the tendency of adsorption is higher. That means here the adsorption will be larger, but for this side, let's say the tendency of adsorption will be lower. So in reality, the surface is heterogeneous, all the sides are not equivalent to each other. But in Langmuir isotherm, it is approximated that all the surface sides are equivalent. That means surface is homogeneous. So this is just basically a background or side notes. So let's back to the question here. So so we have to find the volume corresponding to the monolayer coverage. Now using the BET isotherm, we got the value of V mono, which is the volume corresponding to monolayer coverage, is 996 millimeter cube. So option A is the correct option. For further details, actually you can visit the lecture series on chemistry and physics of surfaces and interfaces, and this course is actually running now. The instructor is Professor T.G. Gopakumar from IIT Kanpur. So any doubts? Okay, great. So next week we'll be also solving 3 or 4 questions, and if any particular topic you want me to discuss, just let me know, then we can prepare and then discuss in the next week, in the next class. Okay, then
Sir, adsorption.
yeah.
Sir, adsorption topic.
Okay, then we'll discuss in the next class, right? Adsorption.
Okay, sir.
Yeah. So okay, so if any other doubts, so then I'm just ending this session, and so let's meet in the next week. Okay. Okay, so all these 3 questions are clear now? Any?
Yes, sir.
Yeah. Okay, thanks. So let's meet in the next week, and we'll discuss the adsorption also. Great. Bye. I'm ending this session.
Thank you, sir.
Yeah. Thanks
Thank
for
you,
joining.
sir.